Everything from the phone you're holding to the lights in your room, our entire modern world runs on this invisible force. But what is electricity, really? Well, today we're going to demystify the magic behind the switch. We're breaking down the fundamentals of current electricity. Okay, let's get into it. Think about it for a sec. You flip a switch, and a light just, poof, turns on across the room. It feels instant, right? Almost like magic. But it's not. It's just pure, awesome physics. And in the next few minutes, we're going to pull back that curtain so you know exactly what's happening inside those wires. So to get to the bottom of this, we've got to start with the most basic idea of all. Something is moving. So our first stop is understanding this concept of an electrical flow. So that's something that's flowing. It's electric charge, carried by zillions of tiny electrons. Electric current, which we represent with the letter I, is really just a measure of how much of that charge is flowing past a single point in a wire every single second. That's all that fancy formula I equals Q over T really means. And we measure this flow in a unit called amperes, or, just amps for short. Okay, and this right here, this is probably the best way to think about it. For a minute, just forget electrons and wires and picture a simple water pipe. The current is exactly like the amount of water flowing through it. A little trickle, that's a low current. A massive gush of water, that's a high current. It's seriously that simple. Okay, so we've got this flow of charge. But that brings up a really important question. What makes the charges move in the first place? They don't just decide to go for a jog on their own. They need a push. And that brings us to our second key idea. That push has a technical name, potential difference. But you and I, we know it as voltage. Just think of it as the electrical pressure that gets the current moving. That whole work done in moving a unit charge phrase, it's just a physicist's way of saying it's the amount of energy or oomph given to each little bit of charge to get it from point A to point B. And we measure this electrical push in volts. And this is where our water pipe analogy becomes so useful. If the current is the amount of water flowing, then voltage is the water pressure. A weak pump, that gives you low pressure and a weak little flow. But a super powerful pump, that creates high pressure, forcing a ton of water through the pipe. No pressure, no flow. It's the exact same idea with electricity. All right, so we've got our flow, which is the current, and we've got the push that creates it, which is the voltage. But in the real world, things are never perfectly smooth, are they? There's always some kind of friction, some kind of opposition. There's always an obstacle. In electricity, we call that obstacle resistance. It's basically a property of a material that describes how much it fights back against that flow of current. See, on a microscopic level, as these electrons are trying to stream through a wire, they're constantly bumping into the atoms of the wire itself, which slows them down. We measure this opposition in a unit called ohms. So, what actually determines how much resistance a wire has? Well, it boils down to four main things. First up, the length. A longer wire is like a longer, more crowded hallway for electrons to get through. That means more bumps and more resistance. Second, the thickness. A thicker wire is like a super wide open hallway. It gives the electrons way more room to move, which means less resistance. Third, temperature. For most materials, making them hotter makes their atoms vibrate like crazy, getting in the way of the electrons even more and jacking up the resistance. And finally, the material itself. Some materials, like copper, are basically super highways for electrons. They have very low resistance. Others, like iron, are more like a bumpy dirt road. Okay, so we've met our three main characters. We've got the flow, the push, and the obstacle. Now, for the really cool part, the one beautifully simple rule that connects all of them. And that rule is the famous Ohm's law. Now I know, the official definition here sounds a bit stuffy. But what George Ohm figured out is actually incredibly simple. All it really means is that the more push or voltage you apply, the more flow or current you're going to get. It's a perfect cause and effect relationship, as long as the obstacle, the resistance, stays the same. And this perfect relationship gives us what is probably the most important equation in all of electronics. V equals I times R. Voltage is just current multiplied by resistance. This isn't just a random formula. It's the key that lets us actually predict and control electricity. If you know any two of these things, you can always find the third. And hey, here's a fantastic little trick to make using that formula an absolute breeze: the Ohm's law triangle. All you do is cover up the thing you want to find, and the triangle literally tells you what to do. Need to find voltage? Cover up V, and you're left with I next to R. So, I times R. Looking for current? Cover up I, and you see V over R. It's so simple. And listen, this isn't just some abstract theory. This is the exact kind of setup scientists and students use in labs everywhere to prove that Ohm's law is the real deal. Let's connect what we've learned to this picture. You see the battery? That's our voltage source, our push. That component labeled R is the resistor, our obstacle. And the ammeter measures the flow of current, while the voltmeter measures the push happening right across that resistor. See? It all comes together perfectly.
All right, enough theory. The real test of whether you've got it is seeing if you can apply it. So let's make this practical and just run through a few quick problems to see Ohm's law in action.
Okay, challenge number 1. We need to find the current. We're given a voltage of 3 volts and a resistance of 5 ohms. So we look at our triangle, or we just remember the formula, I equals V divided by R. We just plug in the numbers, 3 divided by 5, and we get our answer, 0.6 amps. See? Not so bad. Let's do another one. This time, our job is to find the voltage. We're told there's a current of 3.2 amps flowing through a 50 ohm resistor. The formula for voltage is V equals I times R. So we do the math, 3.2 multiplied by 50, which gives us a total electrical push of 160 volts. Done. And for our last problem, let's hunt down the resistance. So a 12-volt battery is pushing a current of 2 amps. What's the obstacle? Well, our formula is R equals V divided by I. So 12 divided by 2 tells us the resistance in that circuit is exactly 6 ohms. Easy. So when all is said and done, what's the big takeaway here? It's that the whole complex world of electricity is really just a simple, elegant dance between 3 main ideas. The flow, that's current, the push, that's voltage, and the obstacle, that's resistance. The second you truly get how those 3 interact through Ohm's law, well, you've basically unlocked the heart of how electricity works. Hey, if this explainer helped things finally click for you, make sure you hit that subscribe button for StudySlide, because we do more of these quick breakdowns all the time. And if you really want to master this stuff, we've put some detailed notes and extra practice problems for you down in the description. Thanks for watching.